It's one of the costliest designing ventures ever attempted, costing $1 billion. However, for it to realize its full potential, which is nothing less than revising the historical backdrop of the universe and reshaping humankind's place within it, many factors must come together perfectly. Today, I will discuss the James Webb Space Telescope, JWST, which is expected to provide answers to many of the fundamental questions that have occupied astronomers for the majority of the last 50 years. It explains how, out of the knot of atoms, stars, galaxies, black holes, and planets that make up the universe, the parts fundamental for life emerged and came together to form this place we call Earth. Is it possible that the conditions that supported this thriving environment may have occurred by chance? The vibrant surroundings that encompass the JWST facility serve as a constant reminder of the Space Telescope's objective: to assist scientists in their efforts to comprehend how we got to where we are today. When it looks into space, it will observe frightening magma planets with molten surfaces that orbit their suns in mere minutes. It will analyze planets that have somehow managed to escape the catastrophic death of their stars and are now circling the remnants of those celestial bodies. It will examine the atmospheres of gas giant planets, search for infant worlds within the dusty disks surrounding young stars, and study a handful of small rocky worlds that may or may not be habitable. Before it can accomplish all of this, JWST must first survive a harrowing journey into space, followed by a sequence of events that have astronomers worldwide excited about the solar system. Apart from investigating planets beyond our solar system, scientists are also keen on learning more about the planet we call home. The fact that Earth has liquid water oceans and oxygen makes it stand out from the rest of the galaxy, but these traits seem to be common across the universe. Specifically, Webb's extraordinary sensitivity and resolution will allow us to develop a more complete picture of objects in our solar system by combining data from multiple frequencies and sources, including Mars and the larger planets. Webb complements NASA's existing solar system programs, which include ground stations, orbiters around Earth, deep space missions, and the International Space Station. Webb's exceptional sensitivity and resolution will also allow it to study Pluto and other dim planets in the Kuiper Belt, along with asteroids, comets, and smaller celestial bodies. With Webb's view of the outer solar system, scientists will be able to combine its observations with Cassini's Saturn data to create a more accurate picture of the seasonal weather patterns on the gas giants in the outer solar system. Certain characteristics in the spectra of these planets reveal the presence of trace organics. Using Webb, scientists will gain a better understanding of the trace organics present in Mars' atmosphere and conduct research that will help validate the results of Mars missions. Since then, scientists have discovered numerous exoplanets across all kinds of star systems and continue focusing their efforts on finding smaller, more Earth-like planets. One of JWST's primary applications will be analyzing exoplanet atmospheres to look for signs of life. The first planetary system found beyond our own did not include a main sequence star like our Sun but rather a pulsar, which is a fast-spinning neutron star. The Webb telescope, on the other hand, is an infrared instrument. But what role does this play in the examination of exoplanets, and how does it contribute to the field? The James Webb Space Telescope will use the transit method, searching for a dimming of a star's light when a planet passes in front of it. This is one of the ways it will collect data. Astronomers refer to this as a transit, and joint efforts with ground-based telescopes will aid in measuring the masses of planets using the radial velocity technique, which involves observing the stellar wobble caused by a planet's gravitational pull. Afterward, Webb will use its instruments to perform spectroscopy of planetary atmospheres, followed by additional collaborations with ground-based telescopes. Webb will also be equipped with coronagraphs, enabling direct photography of exoplanets close to their host stars. Though the resulting image may be just a point on the surface of an exoplanet rather than a vivid landscape, scientists can learn a great deal from that point. For instance, they can study the planet's color, seasonal changes, rotation, weather conditions, and more. Spectroscopy, the study of measuring light intensity at various frequencies, is essential for understanding the constituents of exoplanet atmospheres. When a planet transits in front of a star, the starlight passes through the planet's atmosphere, leaving a fingerprint in the form of absorption lines. These lines reveal the presence of elements and molecules, such as sodium, methane, or water, in the atmosphere. Infrared observations are particularly useful because molecules in exoplanet atmospheres exhibit the most spectral features at these wavelengths. The ultimate goal is to find one of the countless planets in the Milky Way with an atmosphere similar to Earth's. As has been the case with many of humanity's most ambitious research and engineering endeavors, the journey to the launch pad for the James Webb Space Telescope has been plagued by technical delays and escalating costs. However, if everything goes as planned, this flagship telescope, regarded as the successor to the iconic Hubble Space Telescope, should yield a feast of scientific discoveries. The telescope's name has been a subject of controversy in recent years, but its unparalleled sensitivity will allow its enormous golden eye to detect the faint, distant signals left by the earliest stars and galaxies that shaped the cosmos. Once fully operational, its capabilities will include observing alien worlds and potentially detecting signs of life, even though this was not its primary purpose. The James Webb Space Telescope will primarily observe the universe in infrared light. Interestingly, it wasn't until 1992 that the first exoplanets were discovered. Back when the observatory was first conceived, no one even raised the possibility of there being other planets in the universe. It wasn't until much later that humanity realized the existence of exoplanets, and the James Webb Space Telescope is set to transform our understanding of them. The James Webb Space Telescope, JWST, is intended to change how we interpret the universe. While its essential mission is to focus on deep space, its true potential extends beyond just exploring the distant universe. Webb's infrared capabilities are expected to provide insights into the very earliest moments of the universe, well before our planet or even our sun existed. The first galaxies, which formed after the Big Bang, have remained shrouded in mystery for billions of years. Using JWST's exceptional sensitivity, astronomers will be able to peer back in time to observe the formation of these galaxies, stars, and planetary systems. One of JWST's most groundbreaking capabilities is its ability to study the formation of galaxies and the evolution of the early universe. By observing the universe in infrared light, JWST can look through vast clouds of cosmic dust that often obscure objects in visible light. This is crucial for understanding the processes behind the birth of stars and galaxies, as well as for investigating the evolution of supermassive black holes, thought to exist at the centers of most large galaxies, including our own Milky Way. The telescope's ability to study these black holes, their accretion disks, and the gas surrounding them will provide insights into the extreme conditions of the universe's earliest stages. Additionally, the telescope's ability to detect the faintest infrared signals makes it especially useful for identifying the earliest galaxies and stars. These signals will be key to understanding the cosmic dawn, when the first light in the universe emerged nearly 13.5 billion years ago. JWST will capture the light emitted by these first stars, providing valuable information about the conditions that existed in the early universe and how the first elements, such as hydrogen and helium, evolved into more complex atoms and molecules. This is critical for answering questions about the origins of the elements that make up our universe today. The JWST's primary mirror, a giant 6.5-meter segmented mirror, is one of the largest and most advanced optical systems ever made. This enormous mirror is essential for gathering the faint light emitted by distant objects, such as the first galaxies, and focusing it onto the telescope's instruments. Each of the 18 hexagonal mirror segments is made of lightweight yet durable materials, coated in gold to maximize the efficiency of infrared light collection. This complex design allows JWST to achieve far higher resolution and sensitivity than previous space telescopes. In addition to its optical design, JWST is equipped with 4 main instruments, each with specific tasks to study the universe. These instruments include the Near-Infrared Camera, NIR-CAM, the Near-Infrared Spectrograph, NIR-SPEC, the Mid-Infrared Instrument, MIRI, and the Fine Guidance Sensor, FGS, / Near-Infrared Imager and Slitless Spectrograph, NIRIS. Each of these instruments will work together to capture a wide range of data, from high-resolution images of distant galaxies to detailed spectroscopic analyses of exoplanet atmospheres. The MIRI instrument, for example, will be crucial for studying colder objects in the universe, such as newly formed stars, faint galaxies, and even asteroids in our own solar system. Since MIRI operates at extremely low temperatures, it will be cooled by a special cryocooler system to maintain its sensitivity in the mid-infrared frequencies. This will allow scientists to study the most distant objects ever observed, many of which are too faint or far away to be detected by other telescopes. Beyond its scientific contributions, the James Webb Space Telescope is also a symbol of global cooperation. The project was led by NASA, with contributions from the European Space Agency, ESA, and the Canadian Space Agency, CSA. This collaboration has brought together the expertise and resources of multiple nations, each contributing critical technologies and instruments to the mission. The telescope's development, launch, and operation have been a testament to the power of international partnerships in advancing our understanding of the universe. Although the launch of JWST, initially set for late 2021, faced delays, it marked the culmination of decades of work. The telescope's journey into space is equally ambitious, as it will travel to a point beyond Earth's orbit known as the second Lagrange point, L2, located approximately 1.5 million kilometers from Earth. L2 is a stable location where the gravitational forces of the Earth and Sun balance each other. This location provides a clear, unobstructed view of the sky while offering a stable environment for the telescope to operate. Once it reaches L2, the telescope will undergo a carefully planned series of deployment steps, including the unfolding of its large sunshield. This sunshield, about the size of a tennis court, will protect the telescope's instruments from the sun's heat and maintain the extremely low temperatures required for infrared observations. Another remarkable feature of JWST is its ability to study the solar system in unprecedented detail. By observing planets, moons, asteroids, and comets within our own solar system, the telescope will provide new insights into the formation and evolution of these objects. For example, it will be able to analyze the atmospheres of planets like Mars and Venus, searching for clues that could hint at past or present habitability. The telescope will also be capable of investigating the surface composition and weather conditions on distant moons, such as Europa or Titan, which are considered prime candidates in the search for extraterrestrial life. JWST's ability to study exoplanets in detail is another area where it will make significant contributions. By examining the atmospheres of planets outside our solar system, scientists hope to determine whether any of these worlds are capable of supporting life. The telescope's spectroscopic capabilities will allow it to detect trace gases like oxygen, methane, and carbon dioxide in the atmospheres of exoplanets. These gases are considered potential biomarkers for life, and their presence could be a strong indication that a planet is habitable. As we look toward the future, the James Webb Space Telescope is poised to become one of the most important scientific tools ever created. It promises to answer fundamental questions about the origins of the universe, the formation of galaxies and stars, and the potential for life on other planets. Through its observations, we will gain a deeper understanding of our place in the universe, and the mysteries of the cosmos that have eluded us for so long will gradually begin to unravel. The discoveries made by Webb will not only advance our knowledge of the universe but also inspire future generations of scientists and engineers to continue pushing the boundaries of space exploration. The James Webb Space Telescope, JWST, represents a leap forward in space exploration, not just in its technological design but also in its potential to answer some of the most profound questions about the universe. One critical aspect of its mission is to help us understand dark matter and dark energy, two of the most elusive and mysterious components of the universe.